So to find the condition of contractive interference, we consider two scattered separate by a lattice vector T. Okay, this is one lattice point. This is another lattice point. And if you remember from first chapter, I told you that how to relate two lattice points through one translational vector T, where T equal to N1A1 plus N2A2 plus N3A3, right? So for this case, T equal to, if this is just F, so F, so just 1A1 lah, okay? So T is the translational vector. Then this is an incident ray. Then K prime is the reflected ray. Okay, K prime is the reflected ray. Therefore, what is the distance of this distance? So this distance will be K dot product with T, right? Sorry, K prime dot product with T, then you get this one, right? Okay, so this is K prime, this is T. So T dot product with K prime means that you will get this distance. Why? Because we actually reflect this T into this distance. This is from vector, okay? If you can't understand, then maybe you can just Google it. How does vector work? So if I have K in this direction, and then I have T in this direction, if I want to find the distance from this point to this point, I can use that T dot product with K. Okay, I will get this distance. And then how about this distance? For this distance, I can use T dot product with negative K. Why negative K? Because K is in this direction. But for this case, you want to reverse the K into this direction. So this direction will be negative K. Okay, then T dot product with negative K, then you will get this distance. And now the path difference will be K dot T plus negative K dot T. Okay, so K prime dot T plus negative K dot T. So this is the path difference. So let the X-ray are incident from infinity along the direction K prime, K, with the wavelength lambda and the wave vector K equal to 2 pi over lambda. We assume that the scattering is elastic. Elastic means that they have the same energy before and after. Okay, no energy changing, no wavelength changing. For the example, the X-rays are scattered in K direction with the same wavelength. Whenever the wavelength is same, then the energy should also be the same. So that the wave vector K equal to 2 pi over lambda K prime. Okay, the concept of the contractive interference. So if both are in the same phase, then you will get the double value. If both are anti-phase, then this one add with this one you get 0. The top add with negative you get 0, so we get flat line. Okay, so in order to get this double value, the specific direction and specific wavelength should be fulfilled as according to the 2D sin theta equal to n lambda, the Bragg law. Okay. So the simple Bragg law told us that, okay, from this is one lattice point, another 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 lattice point. Okay, so the distance, this is one plane, this is another plane. You see that? Then the distance between these two planes is d, and then based on the Bragg law, it says that all the atoms on the same plane should interfere. Okay, so interfere, and then by using the specific angle and wavelength of the X-ray, then we can get a contractive interference. Okay, so you can see that the X-ray hit is atom and then reflect. The other X-ray, because X-ray have the same parallel direction, hit the second layer atom and then reflect. But then these two rays have different different length. Okay, so here to here is equivalent to here to here, and here to here equivalent to here to here. But then for the second layer, it have extra part. Okay, so the extra part, this extra part is 2d sine theta must equal to n lambda. Why it must equal to integer of the lambda? Because you see that if this is a wave, these two waves must be in the same phase, right? Because they come from the same source, they must be in the same phase. And then when it interact with at this point the electron in the atom, then it has been reflected. So the second layer should also be the same phase. If these two have the same phase, then you will get the superposition. But then if these two are opposite phase, then you will get zero, nothing. Okay, when you get nothing, then there's no interference, there's no constructive interference. Okay, so in order to get the constructive interference, these two must also in phase. Okay, then the problem here is this part difference. So this part difference must always have a full integer of wave, so that these two can be in phase and these 2 points can be in phase. Can be in phase means that this point and this point must have the same phase, same phase, and this point and this point should also have the same phase. Let's say if this is not the full wave, but this is 1.5 wave, then okay, this is 1.5 wave, so 1.5. So you can see here, it's not correct because the wave out should be something like this. So it is 1.5, 1.5 wave, 1.5 lambda. Then this one become anti-phase. Anti-phase, then the resultant outcome will get 0 because these two will get destructive interference. I repeat again. Okay, I use other color. This point must be same phase with this point. Okay, and then this point must be same phase with this point. So now the problem is this additional length. For this additional length, it must be equal to the wave number. If it's not the wave number, let's say like it's 1.5. So 1.5. So this one